I think you need to switch on your, okay, right now it's okay.
Okay. Good evening, everyone. Today, I will introduce some of my researches. It's my honor to share my researches with you. That is the event-triggered adaptive dynamic programming for solving differential games of nonlinear systems. First, I will introduce the adaptive dynamic programming method. Then I will talk about something about the network control and the differential games. Then I will present one of my researches, that is solving for multiplayer nonzero-sum games and the event-triggered mechanism. At last, I will introduce my future work. First, let's recall the knowledge of dynamic programming and reinforcement learning. They are both the optimal method. Consider the system 1.1, then give the performance index at 1.2. Based on Bellman optimality principle, then we can derive the optimal control at 1.4. Actually, these four equations form the basic framework of dynamic programming. Dynamic programming is a kind of backstepping method. It can solve the optimal control problem with closed set constraints. However, the characteristic light computes iteratively and successively from back to front, and requires for storing large amount of data, which may well result in the infamous curse of dimensionality. Reinforcement learning is a vital branch of machine learning field. It is a very hot spot. The processed data only include the model score, where what the model should output is unknown. Thus, it's required for the algorithm to search for the model of which the score is highest. Adaptive dynamic programming is my main focus. It's a approximate optimal method, which is derived from dynamic programming, reinforcement learning, function fitting, and other techniques. The key speed rate is to fit the optimal performance index with function approximation model, such as neural networks, such like the closed form solutions from Hamilton-Jacobi-Bellman equation can be approximated. Owing to the utilization of neural networks on fuzzy approximation model, there is no need for the computing on storing superabundant intermediate data when implementing this method. Therefore, the difficulty of curse of dimensionality can be skillfully overcome. Here, we give the algorithm framework of ADP method. That is, it includes critic model, act module, and dynamic system module, which can be achieved by critic network, act network, and model network, respectively. The critical network is used for approximating the cost function, where the actor is for control law. With the design of model network identifying systems dynamics, the closed loop is derived with neural networks. The critic and actor can be viewed as an agent, and the dynamic model is the controlled plant. Here, we give some ADP methods of different frameworks. They are heuristic dynamic programming, dual heuristic programming, and some other frameworks. They are action-dependent HDP, action-dependent DHP, globalized DHP, action-dependent GDHP. It's noted that although the control precision may be improved with the increase of complexity of creating a network framework, the increase of algorithm complexity and the calculation amount will lead to the decline of computation speed and the superabundant consumption of computation resources. Therefore, some researchers have attempted to simplify the algorithm framework and proposed the method of single critic network, such that the targets can be achieved that include reducing algorithm complexity, increasing computation speed, and reducing the occupation for computation resources. Based on the iteration mode, we can divide the ADP method into two classes. They are first the policy iteration, then the value iteration. Researchers about ADP have achieved abundant theoretical results. It can be used in different fields. For example, the optimal control for constrained nonlinear system, the optimal tracking problem, the robust optimal control problem, and the differential games. Now, the researchers about ADP is on the way to practical applications. Let's think about the question: what can we do with ADP method? We can use ADP to solve the wastewater treatment control problem and the optimal scheduling problem for power system, and the renewable energy scheduling problem, and the automatic drive and the traffic control problem. Now, let's see the event-triggered mechanism. In industrial control environments, the computation resources and communication bandwidth are often constrained. To improve the utilization of these resources, the control signals are recomputed and updated only when the predetermined condition is satisfied to reduce the frequency for information update and exchange. This control approach can be called event-based control. Compared with the time-based classic mechanism, where the design or triggering condition, the event-triggered mechanism can obviously mitigate the consumptions of computation and communication with little effects on system performance. Hence, the event-based control has attracted considerable attention. For overcoming the difficulties like the bandwidth and the resources are constrained, event-based ADP methods have been proposed to solve various optimal control problems. The researcher KG Valdakis has made pioneering contributions in the applications of the event-based ADP method. Then more research results have been reported, especially for event-based control problem for the system with dynamic unknown. Here, we give the block diagram for event-triggered mechanism. From the figure, we can see that the actor, the critic, and the model they work cooperatively to form the basic framework of ADP method. Then the zero-out holder is the key of successfully implementing the event-triggered mechanism. Then let's talk about something about the network control and the differential games. With the development of embedded technology, computer technology, communication technology, artificial intelligence, and other technology, network control, of which the number of controllers is more than one, has attracted considerable attention and changed everyone's life. In some ways, not only the distances among persons are becoming shorter, but also the distances among things, which can be endowed intelligence and viewed as agents. Today is an age full of network and intelligent control. However, to achieve a great network control, we may by means of differential games. Differential games theory is a vital branch of economics. It studies team cooperation, personal conflict, and other complex decision behavior, and has been broadly applied in industrial manufacture, commercial activity, and so on. According to the number of players, differential games can be classified as two-player games and multiplayer games. More precisely, from the relationships among the players, differential games can be divided into zero-sum games and non-zero-sum games. Zero-sum games, the relationships between the players is opposite, which reflects like the improvement of the performance index for one player will certainly decline light for another. The balance between the index for every player can be achieved after sufficient competition. Zero-sum games exist in our life everywhere. For example, the chess, some computer games, and the football game. The football game is a complex differential game, but the penalty kick is a zero-sum game. Non-zero-sum games, the relationships among players become more complex, but not opposite. Every player attempts to maximize its personal revenue when pursue the common goal for all players. Non-zero-sum games can be further divided into cooperative games and non-cooperative games, depending on whether there exist cooperative relationships among these players. For example, properly speaking, the players in the same football team often fight for a common target. That forms a kind of non-zero-sum game. In fact, the football game is a very complex game. It's a mixed differential game because there exist both a zero-sum game and a non-zero-sum games. Differential games provided a novel theory foundation for adaptive dynamics to solve optimal control problem of networked system. The H-infinity control problem of nonlinear system can be transformed into zero-sum games first. Then the Hamilton-Jacobi-Isaacs equation can be solved via ADP method. The optimal control problem for networked system with multi-controllers can be solved by using ADP method to search the approximate solution of Hamilton-Jacobi equations. Based on differential games, ADP method can be expanded to solve control problems of the following system. For example, the control problem of large-scale interconnected system, the optimal control of wireless networked control system, and the consensus control of multi-agent systems, and the robust control of nonlinear system, and the optimal tracking control of nonlinear systems. Then I will present one of my researches, that is solving for nonzero-sum games and the event-triggered mechanism. The notices are as follows. First, we utilize the identify critic algorithm framework to solve nonzero-sum games or the nonlinear system with complete dynamics. Then we construct the critic update law with the concurrent learning technique and stability term to improve the utilization of data, relax the persistent exciting condition, and relax the requirement for initial admissible control. Finally, we propose the event-triggered mechanism with the pre-positive dead zone technique to further mitigate the occupation and the consumption for bandwidth and computation resources. Let's see the problem formulation. We consider the system with multi-controllers. Then we give the performance index for the case player. Then we can derive the Hamilton function. Based on Bellman optimality principle, we can derive the optimal control for every player. Then the coupled HG equations can be reformulated. Note that this equation is a partial differential equation with coupled terms. It's very hard to find its analytical solution, but we can use ADP method to approximately solve it. We derive the event-triggered control. First, we need to construct the time sequence to store all the triggering instance, and we consider the error between the real-time state and the latest event state. Based on Bellman optimization principle, we can derive the event-based control. Since the system dynamics is unknown, we design the identifier network to reconstruct the system dynamics for the following discussions. In this work, we use the neural network to approximate the optimal performance index. We can derive the event-based Hamilton function. This is the foundation of the ADP method. Here is one of our novelties. Differing from the classic update law, only use the current date. Our critic update law is consistent of three terms. Both the current date and the historical date are utilized to relax the persistent exciting condition and the requirement for the initial admissible control. First, we use the gradient descent technique to derive the first update term. Then we based on concurrent learning spirit, we can derive the second term. Finally, in order to make the system more stable, the third term is designed as follows. Here is the judge function. The judge function is used for activating the stability term. When it judges that the system is facing the risk of instability, the third term is activated to help the system to be stable. Integrating the three terms, we derive the novel update law. Here, we give the event triggered mechanism we have proposed. To further mitigate the computation and communication burdens, the triggering mechanism integrates the data zone operation. Here, the DO is the parenticide of positive threshold, determining whether terminates the judgment for a triggering event. Then we give the main theorem in our work. Consider the network control system. The identifier and critic are constructed based on 3.12 and 3.21 respectively. Then all the signals of the closed loop system are uniformly ultimately bounded if the following condition is satisfied. In our method, only when the condition is satisfied, the control for every player can be recomputed and updated. But due to the utilization of the data zone opposition, when the control precision is achieved, the control strategy will not be updated, even when the triggering condition is satisfied. Then the system resources can be further saved. To verify the proposed method, we consider the following nonlinear system. Here, we give some simulation results. Figure 1 shows that the evolutions of system states. Figure 2 shows the event-based control strategies for every player. Then, Figure 3 reveals the triggering condition. Figure 4 shows that compared with the time-based method, our proposed method utilizes less data to recompute and update the strategies. More precisely, our method only uses 500 data, where for the time-based method, the sampling number is 4,000. That's a great improvement. Finally, I wanted to talk about my future work. In the future, I will take time delay into consideration, since there often exists a time delay and packet dropout phenomena for network system with multi-controller. Then I will consider the network system interfered by stochastic process, and I will improve our proposed adaptive optimal method and extend it to solve the consensus control problem for multi-agent system, since I think the multi-agent system is another promising direction. That's my introduction today. Thank you very much.
Okay, thank you for Dr. Liu's sharing. Okay, do you have any questions you want to communicate with Dr. Liu?
Yes, I have a question.
Yes, please.
Okay, so thank you, Dr. Liu, for your speech. It's very interesting, your work about this kind of control. So I have a question regarding the stability condition that you present on the slide 38. You're talking about a condition for the stability or for the bounded for the signals of the control system. So my question is, if these conditions still remains for the case of systems with a fast constant times, or maybe the computational burden can be a problem in the case of a system with a fast time constant. So this is my question.
Excuse me, can you say it again, please?
Can I repeat the question?
Yes.
Okay, so my question is about the stability condition that you pose on the slide number 38. On this slide, you propose a condition to guarantee the bounded signals for the control systems. Okay, so my question is that requirement still apply for system with a fast time constant, or if there are some requirement for the computational borders in this special kind of systems with a fast time constant?
I think the network may be not very good. I can show my email, and I think we can contact this question in the future.
Okay.
Okay. Maybe I can translate a little bit. It's okay.
Okay.
Okay. Okay, Professor Marilla, can I translate a little bit in Chinese? Okay.
Okay. Thank you, Xin.
OK， 那个刘博，他是这个意思，我的理解哈，他就说你这个signal control system， 你的这个信号控制的这个系统，他问有没有这个 requirement for， 就是有没有什么这个什么有你里面有一个什么 faster time content， 是不是有一个快速的那个？你这应该是你们的专业名词吧 ？faster time content。他就说你这个信号的这个系统，有没有可能就是在用到这个你们的这个 faster time content 的这个里面的有没有什么要求，或者是一些什么要求对于那个边界啊什么的有没有什么要求？你可以给大家讲一下，就是说你运用的这个系统，有没有什么要求针对性的这种要求之类的，在这个 faster time 啊。
好 ，OK。Our research is now focused on the theory research. I think there are no requirements for this, and we have attempted to extend our method to applications such as multi-agent systems.
Okay. So thank you, Dr. Liu. So maybe if you can share your email, maybe we can discuss more closely about the stability conditions of your algorithm. So thank you very much.
Okay, I think there are someone else to have a question, right?
Hello, Dr. Liu. Can you hear me?
Okay.
Okay, thanks for your wonderful lecture. I'm very interested in this kind of online learning algorithm applying in the differential game system. And I have some questions to be clarified. That is the multiplayer network systems you have mentioned are the systems without disturbances. But in the practical applications, there often exists some disturbances. How about the effect when using the ADP algorithms or the event-triggered ADP algorithms to deal with the optimal control problem for the multiplayer systems with interferences? Thank you.
Okay. I think it's a good question. In practice, the system are often interfered by the stochastic disturbance. So consider the disturbance is very meaningful. Actually, for nonzero-sum games system, it's often very hard to deal with the HGA equation because there are not only partial derivative terms, but coupled terms. Fortunately, we can use ADP method and some other mathematical operations to deal with this difficulty. But when there exists some disturbance, the situation becomes more complex. But we still have some techniques to deal with it. However, this is just the case of time triggering. As far as I know, there is little work on the network control for the network system with disturbance under the event trigger mechanism. Since this situation is too complex, but as I said before, the disturbance on the network control system and even under the event trigger mechanism is of great significance. In the future, I will attempt to solve it. Besides, some control problems of the network systems are the ones that can be deemed as mixed zero-sum and non-zero-sum games. How to solve this kind of problem depends on how to formulate the performance index functions. This requires more skills. That is another interesting direction.
Okay, I got it. Thanks for your explanations.
Okay. I think thank you for the question, and thanks our Dr. Liu again. Okay, I think it's a bit late in Ecuador, and because of the time limitation, okay, I think it's time for us to see the ending.